Okay, we're starting the topic integration. Okay, so integration is part of calculus along with differentiation. We know that differentiation is all about finding gradient on curves and tangents. Okay, now integration is linked to something else that we'll talk about when we get about halfway through the topic. The first thing that we're going to do, just like we did with differentiation, is get used to the rules. Okay, so some of this stuff will seem quite familiar to you in terms of the operation for differentiation, which is to bring the power down, multiply, take one away from the power. Okay, so something that rolls off the tongue just as quickly with integration. Okay, so let's look at that just now. Okay, now the first thing, let's talk about what the symbol is that's telling you an equation that you're going to integrate, and it's this symbol here. Okay, so that symbol there indicates that you're going to integrate. So let's say we start with x to the 7, and I'm going to put this dx next to it, and that just is another indication that you're going to integrate the function. Okay, so the function that we're going to integrate then is x to the power 7. Okay, now for differentiation, the rule for differentiation is you bring the power down, you multiply, you take one away from the power. Now, for integration, you add one onto the power, you divide by your new power, and then you put this thing on that's called plus c. Okay, so I'm going to talk about this wee bit in a second, the plus c, but let's just concentrate on the numbers. Okay, x to the 7. So what do you do for integrating? You add 1 onto the power, 7 becomes 8, and you divide by your new power, and then you add on the constant of integration. Okay, now what's constant integration? That's this bit that's marked as plus c. Now let me just talk to you about where that's coming from. Okay, so integration is the inverse operation to differentiation. Now what I mean by that is if you've got a function, if you then differentiate the function, well, whatever you get then, if you then take that answer and integrate it, it will bring you back to the start. Okay, so it's like the opposite operation. So if you've got a function, you differentiate it, you've got a new function. If you get that function and integrate it, it's like working backwards, you're back to where you start. So what we would say is that those are opposites or maybe inverse operations. Okay, so let's think about, for example, that in action. Okay, let's say I had f of x and f of x was equal to x to the 5. Okay, so if I differentiated that, I would get 5x to the 4. Now if I then took 5x to the 4 and integrated it, so what's the integration again? So you add 1 onto the power and you divide by the new power, those two cancel out and leave you with x to the 5. You can see that we're back to where we started, which was x to the 5. Now, what's this bit that I'm marking as plus c? That's called the constant integration. Where does that come from? We're going to talk about that just now. Now, I want you to imagine that we had a function f of x and it was x to the 6. And over here we've got a separate function which is x to the 6 plus 4. Now we're going to differentiate both functions. So you differentiate that, you bring the power down, multiply, take 1 away from the power, you get 6x to the 5. You differentiate this one, you bring the power down, you multiply, take 1 away from the power, 6x to the 5, and then if you differentiate 4, it disappears. Now you can see in both cases, when I've differentiated the function, I've got the same result, 6x to the 5 and 6x to the 5. However, my starting point was different. My starting point there was x to the 6, and my starting point there was x to the 6 plus 4. Now the difficulty we've got there is if you differentiate a constant value, it disappears. So that means if you then work backwards to integrate, how do you know if there was a constant value there in the first place? So it would work again if I thought about f of x equals x to the 6 plus pi. Okay, so I differentiate, and I get 6x to the 5, and pi is a constant, so that disappears. 6x to the 5 again, I've got the same result again. Now the same result is came from differentiating 3 different functions. Now the point being then, if we integrate a function, we can't say for definite whether there was a constant or not. So there's a constant pi, there's a constant 4. Now you might say there's no constant with this one to get started. However, you could argue that the constant is 0. Now the point being then is if you integrate a function, you don't know if there was a constant value there to get started with. The reason being is because when that function is differentiated, the constant element of it vanishes. So you can't then predict what the constant value was. So what you do at that point is you just call it plus c. So let's try an example 2. So example 2, we've got x to the 9 and we're going to integrate it. We're going to add 1 onto the power, divide by the new power, and we put on the constant integration. Now at that point, we don't know if that constant integration is there. We don't know if it's 0. It could be 4, it could be pi, it could be anything that's a constant value. We don't know. So what we do is we hedge our bets and we just say, right, it's plus c. Now at that point, plus c can stand for any constant value, including 0. Okay. So let's try an example 3. Remember that the main rule for integration then is you add 1 to the power, divide by your new power. Okay, let's try example 3. We're going to integrate t to the 6. Okay, so add 1 on the power, divide by my new power, add on the constant of integration. Example 4. We're going to integrate p to the minus 8. Okay, so add 1 to the power, p to the minus 7, divided by minus 7 plus c. Example 5. Okay, we're going to integrate g to the 4. Add 1 to the power, divide by my new power, plus the constant of integration. Let's try an example 6. We're going to integrate phi to the minus 11 d phi. Okay, add 1 onto the power, divide by my new power, plus the constant of integration. Okay, let's just toughen up a wee bit and bring in some fractions. Okay, so we're going to integrate x to the 2/3 dx. Okay, add 1 onto the power. So I've got 2/3 and I'm adding on 1. So that's 2/3 of a pizza plus 3/3 of a pizza, which is 5/3 of a pizza. And you can show this working, or you can do it in your head. I would suggest that you get to a position where you're doing it in your head. Okay, so x to the 5/3 divided by 5/3 plus c. Now we can absolutely then tidy this bit up. Remember, from National 5, if you divide by a fraction, you flip the second fraction upside down and you multiply. So I'm going to bring that up and flip it over, and that will be 3/5 x to the power 5 over 3 plus the constant of integration. Okay, example 8. We're going to integrate g to the 1/4. Okay, add 1 to the power, so I've got a quarter of pizza. I'm going to add on a pizza, that's 4/4. 1/4 plus 4/4, 5/4, divided by my new power, plus the constant of integration. Okay, so I'm dividing by a fraction, so change a divide to a multiply, flip the fraction over, bring it up and multiply. 4/5 g to the 5 over 4 plus c, final answer. Okay, example 9. P to the 7/4 dp. Okay, so add 1 to the power, 7/4 plus 1, 7/4 plus 4/4, that's 11/4, divided by my new power, plus c, change the divide to a multiply, flip the fraction upside down. That's 4/11 p to the 11/4 plus the constant of integration. Let's try example 10. Example 10, I'm going to go q to the minus 2/3 dq. Add 1 to the power, so I've got minus 2/3 of a pizza plus a full pizza, so that's adding on 3/3. Minus 2/3 plus 3/3 is 1/3. Q to the 1/3 divided by 1/3 plus c. Okay, bring the fraction up, flip it over, 3 over 1, that's 3. 3q to the 1/3 plus c. Okay, example 11. Example 11, we're going to integrate 5x to the 4 dx. Okay, what's the extra element on with this one, which is a non-unitary coefficient in front of the variable. So 5x to the 4, dead at 0, just do what you think you've got to do with it. Add 1 to the power, divide by your new power, plus the constant integration. To cancel to leave you with x to the 5 plus c. Example 12. Example 12, 2n to the minus 3 dn, add 1 onto the power, divide by a new power, plus c. Okay, so 2 divided by 2 is 1, but 2 divided by 2 is minus 1, so that would just be minus 1n minus n to the minus 2 plus c. Let's try an example 13. Example 13, I'm going to integrate x to the minus 5 thirds dx. Okay, add 1 to the power, minus 5 thirds plus 3 thirds is minus 2 thirds, x to the minus 2 thirds divided by minus 2 thirds plus c. Okay, change the divide to a multiply, flip the fraction, bring the fraction up, flip it over, and it's going to be minus 3 over 2 x to the minus 2 over 3 plus the constant of integration. Okay, example 13, 5x to the 2 thirds dx, 2 thirds plus 1, that's 2 thirds plus 3 thirds, that's 5 thirds, 5x to the 5 thirds, divided by 5 thirds plus c, change the divide into a multiply, bring the fraction up, flip it over, 3 fifths times 5 x to the 5 over 3 plus c, the 2 cancel to leave me with 3x to the 5 thirds plus c. Okay, example 14, we're going to integrate minus 4 theta to the minus 3 quarters. Okay, so add 1 to the power, minus 3 quarters plus 4 quarters is 1 quarter. So that's minus 4 theta to the positive 1 quarter divided by 1 quarter plus c. Bring it up, flip it over. So it's going to be 4 over 1 times minus 4 theta to the 1 quarter plus c. Let's tidy that up now. So 4 over 1, that's just 4. 4 times minus 4 is minus 16. Minus 16 theta to the 1 quarter plus c. Okay, let's try another. We're going to integrate minus 10x to the minus 3 over 2. Add 1 to the power, divide by the new power. Okay, so minus 3 halves plus 2 halves is minus 1 half. So it's going to be minus 10x to the minus 1 half divided by minus 1 half plus c. Okay, so the negatives will cancel each other out. Divide by half is the same as multiplying by 2, so that's 2 over 1, so 2 over 1 times 10 x to the minus 1 half plus c. 2 times 10 is 20, divided by 1 is 20, x to the minus 1 half plus c.